Good morning, advanced algebra students. I hope you are doing awesome. I am really looking forward to doing another lesson with you today. We are going to jump back into our Algebra 2 book. So we are going to pick up now with section 1.6. We did section 1.5 before our detour to the Algebra 1 textbook to talk about solving systems. And today we are going to continue that discussion on how to solve systems, but like I like to say, we are going to supersize that discussion because we learned how to, in chapter 4 of Algebra 1, how to solve a system of two equations using graphing, substitution, and elimination. These systems that we solved in chapter 4 of our Algebra 1 book had two equations with two variables. What we are going to discuss today is how we can solve a system when that system includes three equations with three variables. So at the top of your notes, go ahead and write 1.6 linear systems, and we are going to jump right in with example number 1. All right, so we have three equations, 2x plus y minus z equals negative 10, and negative x plus 2y plus z equals 3, and x plus 2y plus 3z equals 13. So this is a very different scenario than when we just have two equations and two variables. Now I'm going to show you a method for solving this system that has some organizational components to it. The organizational components are technically not required, but I do find them very helpful. So for example, for me, I find it helpful to label my equations as equation 1, equation 2, and equation 3. So I put a 1, 2, and 3 next to the equations, and I circle the 1, 2, and 3. So I know that that's not a number that's part of my equation. That's just the label for the equation. Then what I'm going to do is I'm going to eliminate one of the variables twice because I want to have basically two equations with two variables. The reason I want to do that is because when I do so, then I can solve that system of two equations with two variables the same way I did when I was solving in chapter 4 of Algebra 1. So there are many different possible ways that you can do this, but I like to write down the steps for what I'm doing. So what I want to do in this particular case is I want to add equations 2 and 3. So I'm going to make a note of that on the board here, add 2 and 3. When I do, the x's drop out, and I have 4y plus 4z equals 16. 4y plus 4z equals 16. And I label that as equation number 4. All right, now the next thing I need to do is eliminate x again from one of my equations. Now I already finished working with 2 and 3, so I have to pick a different pair. It can be 1 and 2 or 1 and 3. In this particular case, what I would like to do is I would like to add equation 1 to 2 times equation 2. So I'm going to copy down equation 1 again, 2x plus y minus z equals negative 10. I did not change that equation at all. Now I want to double everything in equation number 2. So I'm going to have negative 2x plus 4y plus 2z equals 6. Notice that I have the instructions for what I did on the board here so that I can make sure not to forget what I'm doing. Again, the x's cancel out, and now I have 5y plus z equals negative 4. 5y plus z equals negative 4, and I'm going to label that equation 5. Again, the labeling is not essential, but I do find it helpful. Now, what we've done is we've created two equations with two variables, and it's the same two variables, y and z. And I can solve this system using graphing, substitution, or elimination. I typically use elimination. So what I'm going to do is write another step here. I want to take equation 4 plus negative 4 times equation 5. So for equation 4, I have 4y plus 4z equals 16. If I take equation 5 and multiply it by negative 4, I get negative 20y minus 4z equals 16. When I add these together, the z's cancel out, and I have negative 16z equals 32, or y equals negative 2. Now, we have done the vast majority of the hard work for this problem. Now that I know that y is negative 2, I can plug this value back into either equation 4 or equation 5 to solve for z. So why don't I just pick equation 4, it's right here, or actually, let's see, let's do equation 5. So we'll do 5 times negative 2 plus z equals negative 4, or negative 10 plus z equals negative 4, or z equals 6. So I have y equals negative 2 and z equals 6. Now I have y and z. I can plug those two values into any of my top 3 equations. Why don't I just go ahead and pick the first one? So I'm going to have 2x plus y is negative 2 minus 6 equals negative 10. And then I'm going to have 2x minus 8 equals negative 10. 2x equals negative 2, or x is negative 1. Now I have solved for x, y, and z. And just like when we're solving a system of 2 variables, we want to put our answer in alphabetical order. So the answer is going to be negative 1, negative 2, positive 6. So if that felt kind of overwhelming to you, it would make sense, because that is a pretty significant problem. Much more difficult than what we did in the Algebra 1 textbook. All right, I have 2 more examples that I want to talk you through. So they're going to be a slightly different topic, but they're all kind of connected. It's mind-blowing to me to think that the Algebra 2 book didn't have any review of solving systems of 2 equations with 2 variables, or it was a minimal review. So I'm glad we took some time out to go back and do that. All right, so this is example number 2. And I'm going to read you the words, but all you have to do is put what I write on the board. Malcolm earns $20 per hour mowing lawns and $10 per hour walking dogs. His goal is to earn at least $160 each week, but he can work a maximum of 16 hours per week. Malcolm must spend at least 5 hours per week walking his neighbor's dogs. For how many hours should Malcolm work at each job in order to meet his goals? So again, look at the last sentence. It says, how many hours should Malcolm work at each job? So let's make X be the number of hours mowing. And let's have Y be the number of hours walking the dog. So now we've defined our variables. Now, what we need to do is set up some inequalities to represent this situation. So it says that he wants to earn at least $160. So since he makes $20 for every hour that he mows, we can say 20x plus 10y is greater than or equal to 160, because he makes $10 per hour walking a dog, and he wants to make at least $160. Now, it says he can work a maximum of 16 hours per week. So that's telling us that x plus y has to be less than or equal to 16. And it also indicates in the problem that Malcolm must spend at least 5 hours per week walking his neighbor's dogs. So y has to be greater than or equal to 5. We also know that the number of hours he's working must be positive. So we can also make x be greater than or equal to 0 and y be greater than or equal to 0. What this tells me is that I'm just going to graph in the first quadrant. So I'm going to set up a graph here to represent the hours that he's working, and we'll have the x-axis be number of hours mowing, and we'll have the y-axis be number of hours walking a dog. Okay, so let's go ahead and start graphing these equations, or inequalities, I should say. So with the first one, I think the easiest way to graph this is the intercepts method. We're going to put a 0 in for x and a 0 in for y. When x is 0, 10 times 16 would give me 160. And when y is 0, 20 times 8 would give me 160. On my graph, I'm not going to skip count. I'm just going to go up by units of 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then I'm going to go out to 6 on the x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I want to graph the point 0, 16 and the point 8, 0. 3, 4, 5, 6, 7, 8. This is going to be a solid line. And because we are going to be greater than or equal to that number, I'm going to shade to the right. Okay, then to graph the inequality x plus y is less than or equal to 16, again, we can use the intercepts method. And obviously, both intercepts are going to be 16. So I have a 16 here and a 16 there. I'm going to connect those two dots. Now, because it says he can work at most, let's see, he can work a maximum of 16 hours per week, we know that this line is going to be shaded below. And again, we're keeping everything positive, so I'm not graphing other than in the first quadrant. The last constraint we have is that y has to be greater than or equal to 0. Now, the equation y equals 5 is just a horizontal line where y is always 5. So I want to shade above that. So this is very similar to our review in the Algebra 1 book, but like I like to say, it's kind of like the Algebra 1 on steroids, because this is graphing an inequality, but it's fairly complex. Our solution is going to be this orange shaded area where all 3 shaded areas overlap. All right, so that is the answer to example number 2 is actually a graph. So any dot in the shaded area or on the border of the shaded area would be considered a solution of this problem. All right, now we have one last example to go over, and it's more of, I would say, probably notes than an actual example, but it is talking about our introduction to something called matrices. So this is pretty much just going to be a few examples of matrices. So let's call this example 3, and then we'll talk about what a matrix can look like. So here's the thing, matrix sounds like a really fancy word, but it is essentially numbers arranged in the shape of a rectangle or a square. So we use matrices to represent linear equations. So let's give an example of a set of linear equations. AX plus BY equals C, and DX plus EY equals F. Now I'm going to do this so you kind of have a generalized example, but I'm also going to put a specific one next to it so you can see it with numbers. So for example, 2x plus 3y equals 1, or 4x minus 2y equals 10. Now, a coefficient matrix is a matrix that just includes the numbers in front of our variables. So for example, in this problem here, the coefficient matrix would be A, B, D, and E, because those are the numbers in front of X and Y. The coefficient matrix for this example here would be 2, 3, and 4, -2. So the coefficient matrix just shows the coefficients of the variables. Now, an augmented matrix augmented matrix shows all the coefficients and constants in the systems of equations. So for our augmented matrix for the problem above would be A, B, D, and E like we had before, and then there's this little dotted line and you put C and F on the other side. The augmented matrix for this example here would be 2, 3, 4, and -2 with the dotted line, and then 1 and 10 to the right of the dotted line. So these are coefficient matrices, and these are augmented matrices. Okay, and then something that we sometimes need to do is so let's actually do one more quick example, is if we're given an augmented matrix, we can be asked to turn it back into a linear system. So let's go ahead and just do that one last example. Example 4. If we were given the augmented matrix here, the question is, what would be the linear system that would correspond to it? So keeping in mind that on the left we have our coefficients and on the right we have our constants, the answer would be x plus y equals 10 and 3x plus 2y equals 80. Now we are going to study matrices a lot more in the next section of the book, and they're going to be super helpful for us in solving systems. But this is just a mini introduction. Thanks so much, you guys. Look forward to seeing you in Zoom.